Begin with welcome to everyone, and I hope this will be a successful lesson. Our lesson today, particle physics, chapter 22, section 4. In this section, we will try to achieve some targets. Number one, we will define the four fundamental attractions of nature: strong, electromagnetic, weak, and gravitational. The second target, identify the elementary particles that make up matter. The third, describe the standard model of the universe. The scientists tried to reach the elementary particles. The elementary particles, which are the fundamental units that compose matter, don't appear to be divisible and have neither size nor structures. And the particle physics seeks to discover the ultimate structure of matters, elementary particles. Now we are gonna to discussing many new particles have been produced in accelerators. Accelerators in 1932, the scientists thought protons and electrons were elementary particles. Electrons and protons were elementary particles. The reason was particles were stable. Particles were stable. But in 1945, experiments at particle accelerators, like these accelerators, the Stanford Linear Accelerator in California, creates high energy particle collisions that provide evidence of new particles. Now, these new particles tend to be very unstable and very short half-life. They're ranging for 10 power minus 6 second to 10 power minus 23 second. And there's more than 300 new particles have been cataloged. There's four fundamental interactions in nature. We have talked about strong, electromagnetic, weak, and gravitational. And you have to understand the properties of elementary particles to be able to describe the interaction between them. And all particles in nature are subject for strong, electromagnetic, weak, and gravitational interactions. The first, the strong interaction, is responsible for the binding energy of neutrons and protons into nuclei, inside the nuclei. And this interaction, which represents the glue that hold the nucleons together, proton with neutrons, proton with proton inside the nucleus, is the strongest of all the fundamental interaction. It's very short range, and is negligible for separation greater than about 10 power minus 15 meters. The approximate size of nucleus greater than the nucleus will be divided. Now, the second, the electromagnetic interactions, which about 10 power minus 2 times the strength of the strong interactions at nuclear distances. There's difference in distances between two interactions. And it's responsible for the attraction of unlike charges and the repulsion of like charges. Unlike charges, proton and electron, for example. And this interaction is responsible for the binding of atoms and molecules. And it's a long-range interaction that decreases in strength as the inverse square of the separation between interacting particles, as described in chapter Electric Force and Fields, Coulomb's law. The third, the weak interactions in the short range nuclear interactions. The range is short. That's involved in beta decay. Its strength is only about 10 power minus 13 times that of the strong interactions, because the strength of an interaction depends on the distance through which it acts. Now, the relative strengths of two interactions differ depending on what separation distance is used. Now we'll see the strengths of the weak interactions. For example, is sometimes set to be as large as 10 power minus 6 times that of the strong interactions. Keep this information in your mind, that these relative strengths are merely estimates and they depend on the assumed separation distance. Finally, the gravitational interactions is long range. It's different. Long range interaction with a strength of only about 10 power minus 38 times that of the strong interaction. Although this familiar interactions is what holds the planets, stars, and galaxies together, its effect on elementary particles is negligible. The gravitational interaction is the weakest of all four fundamental interactions. Now we are gonna to studying how a force can be thought of as mediated by an exchange of particles. In this sections, we have referred to a force as an interaction. This is because in particle physics, the interaction of matter is usually described not in terms of forces, but in terms of the exchange of special particles. And in this case of the electromagnetic interaction, the particles are photons. This means the electromagnetic force is mediated by photons. Now if we look to the figures, we will see the wavy red line represents a photon and the blue lines represent electrons. This means in particle physics, the electromagnetic interaction is modeled as an exchange of photons. And here we can see how two electrons might repel each other through exchange of a photon. Here the momentum is conserved and the electron emitting a photon changes direction slightly. As the photon is absorbed, the other electron directions must also change. Now the net effect is that the two electrons change direction and move away from each other. Likewise, we explained before the electromagnetic force. Now we are moved to the strong interaction is mediated by particles called gluons. And the third, the weak interaction, is mediated by particles called the W and Z bosons. And the last is the gravitational interaction is mediated by gravitons. All of these, except gravitons, have been detected. We can see it. The four fundamental interaction of nature, we can summarize it and their mediating field particles in the figures. Interaction force, number one, strong. Relative strength, 1. Range of force approximately 1 femtometers. Mediating field particles, gluon. Number 2, electromagnetic relative strength 10 power minus 2. Range of force proportional to 1 over r square. Mediating field particles, photon. Number 3, weak relative strength 10 power minus 13. The range of force smaller than 10 power minus 3 femtometers. mediating field particles W, positive, negative, and Z, boson. Gravitational relative strength 10 power minus 38. Range of force proportional to 1 over r square. Mediating field particles is gravitons. Now we have a theory called quantum electrodynamic, or QED. It's defined the interaction of charged particles by the exchange of photons. I repeat, the interaction of charged particles by the exchange of photons. Now, how can we classify of particles? All particles other than the mediating field particles can be classified into two broad categories: leptons and hadrons. Now, what is the difference between leptons and hadrons? Leptons are a group of particles that participate in the weak gravitational and electromagnetic interaction, but not in the strong interaction, except the strong interaction. But the hadrons are particles that interact through all four fundamental interactions, including the strong interactions. So now what about leptons and hadrons? Leptons appear to be elementary, while hadrons consist of smaller particles called quarks. Electrons and neutrinos are both leptons, like all leptons, because it has no measurable size or internal structures and don't seem to break down into smaller units. Because of this, leptons appear to be truly elementary. Now, as a result, hadrons can be further subdivided into baryons and mesons, based on their internal compositions. Leptons, electrons, and neutrinos are both leptons. Hadrons, the strongly interacting particles. Baryons, the most common example of baryons are photons and neutrinos. Now, hadrons include mesons and baryons. If we look here, hadrons include mesons and baryons. Hadrons, the strongly interacting particles. It can be divided into two classes, mesons and baryons. Mesons and baryons were classified according to their masses. Baryon were heavier than mesons, and both were heavier than leptons. Today, mesons and baryons are distinguished by their internal structures. All mesons are unstable because of this. They are not constituents of normal, everyday matter. Baryons have masses equal to or greater than the proton mass. It's approximately equal the proton mass. And there's most common example of baryons are protons and neutrons, which are constituents of normal because everyday matters. Also, hadrons are thought to be made of quarks. There's many facts strongly suggest that hadrons, unlike leptons, cannot be truly elementary. Because in particle collision experiment involving hadrons seem to involve many short-lived particles. This means that hadrons are made up of more fundamentally particles. In addition, there are numerous hadrons, and many of them are known to decay into other hadrons. In 1963, Morigel, Mann, and George Zweig independently proposed that hadrons have a more elementary structures. According to their models, all hadrons are composed of 2 or 3 fundamental particles, which came to be called quarks later. But in the original model, there U, D, and S, these means up, down, and sideways. Now, what is the difference between mesons and baryons? The difference between mesons and baryons is due to the number of quarks that compose them. The number of quarks that compose of them. In these figures, meson, 1 quark and 1 antiquark. Baryon, 3 quarks. Antibaryon, 3 antiquarks. These 6 quarks seem to fit together in pairs. We will put it in pairs. Up and down, charm and strange, top and bottom. And all quarks have a charge associated with them. The charge of a hadron is equal to the sum of the charge of its constituents, quarks, and is either 0 or multiple of E. 0 or multiple of E, the fundamental unit of charge. This means that quarks have a very unusual property, fractional electric charge. We can see, in other words, the charge of the electron is no longer thought to be the smallest possible non-zero charge that a particle can have. Now we can summarize all previous information in the figures. Quark, charge, antiquark. Charge. Up, down, charm, strange, top, bottom. The charge, the suitable charge, antiquark, and suitable charge. What's here? Positive 2 over 3 electron, minus 1 over 3 electrons, positive 2 over 3 electron, minus 1 over 3 electron, positive 2 over 3 electron, minus 1 over 3 electron, and the opposite. 4. Now, antibaryon and antibaryon interact with a meson. Can a baryon be produced in such an interactions? We will answer these questions. The question, can a baryon be produced in such an interaction? Explain. The answer, no, because antibaryon is made of 3 antiquarks, and a meson is made of 1 quarks and 1 antiquarks. Thus, a baryon, which consists of 3 quarks, could not be produced in these reactions. Notes here, meson and baryon, 3 quarks, meson, 1 quarks. Second questions, strong and weak interactions. 2 protons in a nucleus interact via the strong interaction. Are they also subject to the weak interactions? The answer, yes, because although the strong interaction has a much greater effect. Now, if we look to the figures, P positive mean a proton, N mean a neutron, K minus means a kaon, bi positive a pion. Now the quark composition of several hadrons, baryon and hadrons, just two of the quark, U and D. U and D. Baryons, mesons. U and D. Up, down. Now just two of the quarks, U and D, are needed to construct the hadrons encountered in ordinary matters, proton and neutron. The other quarks are needed only to construct rare forms of matter that are typically found only in high energy situation. For example, particle collisions. Now the charge of quarks up, down, up, down. Now plus 2/3 electrons, plus 2/3 electrons, and minus 1/3 electrons. The total charge of the proton is positive E. Proton, positive E. Likewise, the total charge of quarks in a neutron, up, down, down, up, positive 2/3 electrons, minus 1/3 electrons, minus 1/3 electrons. The sum is 0, neutral. Now, physicists believe that 6 quarks and 6 leptons and their antiparticles are the fundamental particles. But in the future, we don't know. Baryon contains 3 quarks, as we know, while mesons contain a quark and an antiquarks. The baryon represented are a proton, B positive, and a neutron, proton and neutron. The mesons shown are a pion and a kaon, K negative. Both are particles. Now physicists believe that quarks are permanently confined inside ordinary particles by the strong force. Now this force is often called the color force for quarks. Color force, color is merely a name given to the property of quarks that allows them to attract one another to form composite particles. The attractive force between nucleons is byproduct of the strong force between quarks.